Go, go.
Welcome to the TCS seminar at Jagiellonian University. Our speaker is Piotr Micek, and his title is Tight Bound for the Erdős-Pósa property for tree miners.
Hi, everyone. Thanks, Tom. Here are my slides. Yeah, good afternoon. So for today, I prepared a presentation on my most recent research activity. This is a joint work with Vida Dujmowicz, with Pat Morin from Ottawa, and with Ben Jarret from Brussels. We did it last month, where we spent an amazing 2 weeks of research in Ottawa. Yeah, so all this is about Erdős-Pósa style of theorems. So there's a number of theorems in combinatorics that are charming because they guarantee the existence of a desired object just because some obvious obstruction does not occur. And perhaps the easiest example is the Hall's theorem about perfect matchings in a bipartite graph. But obviously there are many more, and as humans we are looking for these kind of easy to understand patterns. And the following theorem, named by Paul Erdős and Lajos Pósa, published in 1965, relates to graph parameters. So the largest size of a packing of cycles in a graph, and the smallest size of a hitting set of all cycles in a graph. So one of the classical ways to state the theorem is as follows. So for every integer k positive, and every graph G, either G contains k vertex disjoint cycles, or G contains a small set that hits all the cycles. So small means of order k log k. And when you remove this set of vertices, there are no cycles anymore. So G minus X is a forest. There is a whole industry of research on the so-called Erdős-Pósa properties for families of graphs. So this statement is for a family of all cycles. And once you know that the function exists, like for cycles, you can ask about the asymptotics, or you can ask for a best possible function. So it turns out that k log k is the exact asymptotics. You cannot do better. So the example, the construction witnessing this is a family of high girth expanders. Yeah, so cubic expanders, say. So maybe I won't give you the construction or the exact definition, just to say that this family of graphs, so high girth means that when you have n vertices, the girth is log n. And then one can show that these graphs, they have linear in the number of vertices. So when you study this construction, you will see that if you have k, if the packing number is k, then the size of the hitting set, it must be of order k log k there, and this matches the bound from the theorem. So yeah, so that's the classical theorem. And now let me remind you and myself what is a graph miner. So when I have a graph H, So I can try to look for H in G, and I find it if I can map vertices of H to subgraphs of G. So to connected subgraphs in such a way that two different vertices are mapped to vertex disjoint subgraphs. And on top of that, whenever I have an edge in H, I want the respective two subgraphs to have an edge between them. And then I say that G contains an H minor, or I say that this family indexed by the vertices of H, family of subgraphs of G, is a model of H in G. And then we can have a look at one of the most known Erdős-Pósa type theorems for models of a fixed planar graph, minor models of fixed planar graph. So now we want to fix a planar graph H, your favorite planar graph, like maybe mine at the slide, yeah. And then the theorem says that there is a function, yeah, such that, and again, for every positive integer k and every graph G, either G contains k vertex disjoint subgraphs that each contain an H minor. So in other words, G contains k vertex disjoint models of H, you could say. Or there is a set X of size bounded by the function by f of k, such that when you remove these vertices, you have no H minor anymore. So this is non-trivial. It's a consequence of the grid minor theorem. And it also is a kind of characterization of planar graphs in a sense that it is not true if you take H being non-planar. Yeah, that's a nice exercise actually to find it out. And if you want to project to the first theorem, all you need to do is to take H being a triangle K3, because when you think about a model of K3, then it's a cycle. Yeah. So if you don't care about the function K log K, this is the Erdős-Pósa. This projects to Erdős-Pósa theorem. Okay, so that's a nice theorem. And then since this was the first application of the graph of the grid minor theorem, it's actually published in the same paper, Graph -5, in 1986. The bound was far from polynomial in K. But then, but by now we know the exact asymptotic of the best possible function f for a fixed H. So yeah, first in 2013, Chekuri and Khusroy published a paper with a result that this function is K is almost linear in K. Yeah, K polylog K. And then, so I think they avoided of the direct use of the grid minor theorem. And actually, this paper was just before they published a polynomial version of the grid minor theorem itself. So I think that some ideas are already here, or some ideas from here driven the whole project of the polynomial grid minor theorem, as far as I can tell. Then later on, 2019, Wouter, Kames, Van Wattenburg, Tony Huyn, Vengeray, and Jean-Florent Raymond, they got the right asymptotics. So K log K, which is tight, as I already mentioned, for cycles. So actually, we know all the asymptotic except one case. So here is a kind of wrap up. So if H is non-planar, there is no theorem like that. If H is planar and contains a cycle, then we know that the asymptotic is K log K. So all we should discuss is the case that we don't have a cycle. So H is a forest. And then we know that the function exists, yes, and it's linear. So the fact that we need at least linear and k is somewhat trivial. So yeah, because okay, if you look at this type of statement, either you have k vertex disjoint subgraphs or you hit all. So imagine that you have k minus 1 models of what you're looking for, and just that's your whole graph. So the first item does not hold because you don't have k of them, you have one less. But now, since they are vertex disjoint, you have to hit each of them, and you need one vertex per each because they are vertex disjoint. So you really need at least k minus 1, and this is trivial. You don't need to know anything about the graph that you model. So yeah, so linear is really the best you can get. And this, yes, and this relates exactly to the theorem I want to present here and show you the proof today. So the result is a tight, very tight, not asymptotically, but just tight bound for the case when this graph H is a tree. So how does it read? So you fix a tree T on T vertices, and then again for every positive integer k and every graph G, two options: either G contains k vertex disjoint models of the T, or G contains a set of vertices of size at most, and here we have T times k minus 1, such that when you remove these vertices, there is no T minor. So okay. So why is it fun? Well, okay. First of all, we got really the tight bound. I'll argue that this is absolutely tight just in the next slide. But this is one thing. The second thing is that our proof is actually pretty simple, and I aim to present everything today. Yeah. While the previous linear result was a bit complex, it was basing on some operations in the monadic second order logic. It was a deeper stuff, not the easy stuff I want to present you today. So yeah. So about this tightness. So please just consider G to be, so fix your favorite tree T, it doesn't matter, on T vertices. And then just consider a complete graph on T times K minus 1 vertices. Yeah, just a click. And now, okay, so the first item cannot hold because you just don't have enough vertices to have K disjoint models of T. You need T times K vertices at least. Yeah. And you don't have it. So first item is out. But now, if you want to kill all the models of your T, since you live in a complete graph, you have to remove G minus X has to be of size at most T minus 1, because you have every graph in the complete graph on T vertices. You have everything as a minor there. In fact, in particular, a tree. So okay, so this means that we are starting from T times K minus 1 vertices, and then the target is T minus 1. So you have to remove at least this number, which is exactly the number from the theorem. So this is a absolutely obvious lower bound. Yeah, and it holds. So I will try to now start the discussion and gather like one particular tool that I need to present you the argument, and then I will go with the argument. Well, okay. So the case that H does not have a cycle is about forests, not trees. Yeah, and so for the forest we have this statement. I presented you first the statement for trees because there we claim we know that it's absolutely tight. We don't know what happens for forests. Yeah, we have a very strong bound, again T times K minus something, but we don't know if it's tight or not. But this is actually the theorem I'm going to prove today with you. So let me read with you the statement. So now we have let F be a tree. This should be a forest. Apologies. So we fix a forest F on T vertices, and then I want to then by denote by T prime the size of the maximum component in the forest. So there is a tree which is the largest in my forest, and its size is T prime. Okay, so T prime less or equal T in general. Yeah. And in the case that this forest has just one component, so it's a tree, T prime equals T. Yeah. And now again, for every positive integer k and every graph G, either you have k vertex disjoint models of the forest, happy, or you have a set X, and this set X is now of size T times k, size of the forest times k, now minus not the whole T, but just T prime. Yeah. So it's a slightly larger set. If you, yeah, and that's what we can prove. We actually don't know what is the truth for the forest, if this bound is tight or not. There are some subtleties here that we don't understand, and we leave it open for further research. Okay, so we have the theorem. Now, in order to approach the proof, I have to tell you what is the path decomposition. We're not going to do tree decomposition, so let's just talk directly about paths. So a path decomposition today of a graph G is just a sequence of subsets of the vertices of G, yeah? B1 to BQ. And now this sequence should preserve two properties, two easy properties. One, every vertex of G lies in a, how do you say in English, contiguous, excuse me? Contiguous, yes. Contiguous subset of bags in this sequence, yeah? So you see like vertex A, three bags forming like an interval. Interval is an easier word. And the same the other vertices in my example, yeah? And second property is that whenever you have an edge in your original graph, there must be a bag containing both endpoints. So these corresponding intervals for the vertices have to intersect. Yeah. So yeah. So that's a visualization and a graph and its path decomposition. And then if you do a path decomposition, a tree decomposition in general, you're trying to have small bags. This tells you something about the structure. And the path width for us today is basically the best you can do. So you try to minimize the size of a bag in your path decomposition, and the best you can do is basically the path width with an offset 1. Yeah. So that's the path width of a graph. Now path width is pretty much related to the trees you can find as a minor in your graph G. So if I'm looking at the path width of G, this is one parameter, and the second parameter would be the largest complete binary tree that I can find as a minor in my G. That's the second parameter. Then these two parameters are functionally tied together. Yeah, and the more difficult direction of this bind is stated here. It's a theorem by Robertson and Seymour published in Graph Minors 1, 1983. So there exists a function such that for every forest F on T vertices and for every graph G, if only your graph has large path width. So if only path width of G is some function of the target size of the target forest, then G contains F as a minor. So just large path width forces you to have forest trees as minor. Yeah, and then this function was perfectly understood later on. So in a paper by Beanstalk and others, they show that T-1 is the function, and you can't do it better for obvious reasons. But actually, I will use today as a tool a result by Diestel, who in 1995 he published a simple proof of this theorem with the exact bound, yeah, which was actually, at least in the first version of his graph theory book. Very beautiful stuff. Short proof. Here is the critical lemma from that. I'm not going to reprove that with you today, but this is, again, this is not something that would take a day to understand, more like 20 minutes, yeah? But we will skip that part for today. But let's read together the statement. So G is a graph, T is an positive integer, F is a forest on T vertices. Then, given that path width of our graph G is large enough, at least T minus 1, so already we know that we could find this forest as a minor, but we want more. What we want is that there exists a subset of vertices Y. Yeah, so you can take some subset of vertices of your graph. This is Y. And then just this graph induced by Y, so G of Y, this is how I denote it, has path decomposition with bags of size at most T. So small path decomposition. The graph that we are dealing with can have huge path width, but this little fragment has path width controlled. You have a nice path decomposition. So not only that these bags are small, of size at most T, but the interface of Y. So what is an interface of a set of vertices in a graph? So these are the vertices that have edges outside. So interface or boundary of Y, yeah? So these are these vertices to the right of my picture, yeah, sending edges out. This is the interface. So all the interface of Y is contained in the last bag. Yeah, we have a path decomposition sequence of bags, and all the interfaces in the last bag. So this intuitively, this makes you ready to kind of extend the path decomposition further on. Yeah, to kind of chip off some other fragments of the graph. Yeah. So that's the intuition behind the first property. And the second property is that indeed you have F as a minor, and it's already in the Y part. Yeah. Actually, Diestel proves more here, which is critical, that not only you have a model, but this model overlaps with the last bag. So so each branch set of the model intersects the last bag, or intersects the interface, in fact, of Y. Yeah, but this I don't write it here because I don't need it. We don't need it in this proof. Okay, all we need is that we are leaving behind a model of F. Okay, so this is. Okay, this is a statement, it is tell. And now, with this statement in hand, we'll just prove the theorem. And we go home. So, okay, so that's the reminder of what we are proving here. So that's the version of the forest, yeah. And yeah, let's try. So, we fix a graph G. And now we're thinking about some forest, but now I'm going to make like a technical instance of and a statement of what I really want to prove by induction. Yeah. So instead of talking about the forest, I have like C trees. Yeah. C is a fixed integer. Yeah. And then T1 to TC are trees, and the sizes of T1 TC are T1 TC. Yeah. And let's say that this is ordered. Yeah. So the TC is the largest one, yeah. Now, also I have a vector of x's, x1 to xc, and this is again, I see that I didn't put the definition. This is just a vector of non-negative numbers, yeah, x1 to xc, and then an instance. What I'm calling an instance is this tuple. So a graph. This number of these trees I'm looking at, the trees themselves, and then these counters. So this will the vector of x's should tell us somehow how many models of T1 I want. It's x1. Yeah, this will be some number, maybe 3. How many models of T2 I still want? Yeah, x2. Some of them could be zero. They're always non-negative. Okay, that's an instance. And then since some of the x's in the instance could be zero, I have this set I, which is just a set of indices with positive x's. Those that I still want to find, those trees that I still want to find among. That's it. Okay. So this is a notion of an instance, and now is the statement. There's a question. Yeah, I'm about to state what I want based on the instance. So the statement is here. So for every fixed instance, we're going to prove the following: either you have these vertex disjoint models. So, yeah, so you have a family which is doubly indexed, yeah, by I running from 1 to C, and by J running from 1 to Xi, yeah, and then the subgraph Mij contains a Ti minor, yeah. So how many Ti minors do I have? Xi, yeah. So either G contains like this solution, yeah. So this set of vertex pairwise disjoint models that makes me happy, or not. And if not, then I can kind of hit, yeah. So I have a set X which is of controlled size, and here the size is, as you see, is sum of Xi times Ti minus something, because the final statement has this minus. Then I have to control it here. I have to subtract something. So this is minus T max I. Max I is the maximal size of the maximal tree that has a positive Xi, yeah. So I have a set of X, which is of controlled size, such that when I remove this set, the rest of the graph, G minus X, contains no Ti minor for some I in I. Okay, and this will be enough to close the theorem, because the statement that we have is about some forest. So this forest has C components. Let it be the C. Then the components of these forests we can take. This is T1, Tc, and we can set up the vector of x's to be k. Yeah, and then when we prove this technical statement, either we'll have k pairwise vertex disjoint models of f, just from the first statement over there. And if not, then we have this set x, and now each xi is k. The sum of ti's is exactly the size of the forest, which is t. So this will give me t times k, and we subtract this little thing, which pessimistically, why pessimistic? No, not pessimistically. We subtract the max, which is the size of the largest component. Yeah. So this is the t prime from the statement. So okay. So this was the argument that all we have to do is to prove this statement for an instance, which we're going to approach inductively in a moment. Is there some question? I feel like I'm on the slower side, but there's still.
So the T prime here is the size of the largest component?
Yes. Yes. So this is the this is from the statement, yeah, Michał. So T is the size of the forest, and T prime is the size of the largest component. This is what we are going for. And this part here on this slide was just, we can get it if only we prove the technical statement about instances.
Okay.
Yeah. So, okay, so we approach the proof of the statement, and this we're going to prove inductively on the sum of the xi's. So the base case is when sum of the xi's is 1. So what I assume about the instance is that at least one xi is positive. Yeah, this is what I assume. Yeah. So this is the simplest instance I can get. Yeah. So say the sum of xi's is xm, which is equal 1. So what do we do there? Well, we have to just notice that what we want to prove is absolutely obvious. Yeah. So either G contains Tm minor or it doesn't. That's the depth of the statement. If it contains Tm minor, so this is the item, the first item. Then this is all you need to prove. Yeah. And if it does not contain the Tm minor, then take X to be empty. the question is the size okay? So 0 is less or equal than the whole sum is 1 times the size of this tree, Tm, minus the largest tree in the forest, which is again Tm. This is 0. So okay. So if we just have this, if the sum, if there's just one x which is positive and it's equal 1, then the statement is trivial. So this constitutes the base case. Now, if we make an action step, so we assume that the sum is at least 2. And now for the rest, let's fix the index m to be the min of I. Yeah, this will be handy in a moment, because now we have to discuss the graph G. And there are two options: either path width is large or it's small. So in the case that path width is large, if path width is at least Tn minus 1, we can apply Diestel's lemma. So I will remind you gradually what the lemma was about. But so we apply it for Diestel's lemma is about forest. What we take only Tm. We just look at the Tm. And then Diestel's lemma produces this set Y. Yeah. So just think about Y. If Y has its path decomposition, there is a model of Tm that is closed in Y. Yeah. This will come in a moment. But what do we do if path width is small? Well, if path width is small, let's just take Y to be everything. Yeah. And then let's take a path decomposition witnessing that the path width is small. In either case, we have bound on the path width of GY, and we have a path and also we have path decomposition of GY. So what are the properties of the path decomposition? Well, the bags are, each bag is of size at most Tm. Yeah, this is this condition here. And the interface of Y in the graph G is in the last bag. Yeah, that's the thing we have. Now, to proceed, we have to ask ourselves if we have one of the trees that we're looking for as a minor in GY. This is a yes/no question. And if we do not have it, then the only option was that we actually didn't apply Diestel, because Diestel always gives you Diestel gives you Tm as a minor here. So the only option that the GY doesn't have 3 as a minor was that we were in this case. And Y is everything. Y is everything, and you don't have Ti as a minor for all I. This means that you already have one satisfied. Not one. That should be 2. 2 is satisfied with X being empty. Okay, sorry for that. Yeah, so so no models, easy. So we are in the case. So we are in the case that we do have a model of a tree in GY. Now so now okay, now we are working with it. So we have this path decomposition B1 to BQ, and now okay, Diestel gives us well, we have a tree, but what we want is to get the tree which is kind of leftmost. So we are going over the bags from 1 to Q, and we stop at the index L that completes the first tree of tree as a minor. Yeah. So from B1 to BL, G of B1 to BL, which we will denote by GL, contains one of the trees from I as a minor. And the set, and this graph without BL, with BL removed, doesn't contain any tree. This is the first time we have a tree as a minor. Yeah. So okay, so this is like a visualization how the BL could look like. Yeah, and this tree somewhat sits in the left part of the picture. Yeah. And what is important is that when you remove BL, so you remove this gray set in the figure, on the left side you have no tree as a minor. no tree that you're looking for as a miner. Yeah. Yeah. And so that's good. What do we do? Okay, last tiny bit that I want to observe on this slide is that when we look at the interface of the GL, so GL is the stuff that we have on the left, including the gray. So this is the graph GL. And when I look at the interface with the rest, then what I want to agree on is that it's contained in BL itself. This is like a property of a, well, of a path decomposition and of the fact that the BQ had all the interface to the rest. This is like combination of these two. Okay. So what next? So now, when we have this kind of one model fixed, yeah, which is kind of leftmost on the whole picture, we look at the rest. So we look at G prime, which is G minus GL. So this blue part here. Let's take it all. Yeah. Yeah. So the idea is that we secured one model. Maybe we can call kind of induction and complete the proof. And there's that will be it. So okay. So what can we? So to call induction, we have like a whole setup of an instance. So I have a graph G prime that I want to discuss with you. Let's set up the axis. So the target axis will be the same as before, except this one thing. So the model of the tree that I have here is the model of T alpha. So recall that I have no control which tree do I model there, because I took kind of the leftmost. Yeah, so DSTEL gave me a tree TM, but then maybe some other trees are in the Y, yeah, and I took the leftmost. So I just know that this is one of the trees. I'm calling it T alpha, yeah. So alpha is in I, is an index in I. And now, to create this instance, we have the same values of x's. These are x primes, except x alpha prime, which is one less. Okay. So now we have a nice instance, and it's smaller. So we call induction. So there are two options. Either induction gives us back models. That's option number one, yeah? So we have these vertex disjoint models of what we want, yeah? And now all we have to understand is that what we want are those together with our yellow model, yeah? These blue models that we have are all the models of the trees with the right count, except this one bit x alpha prime, which is one less, but we have the model of T alpha here waiting for us. That was the whole idea. So this is an easy case. So we have to look at the case when induction says, okay, there is a Hitting set. So induction says, okay, there is a set X prime, subset of vertices of G prime, which is of controlled size, and the control is here in red. Yeah, so size of X prime is a sum of I and I prime. So okay, please note that the notion of I and I prime could be different than I, because we decremented one of the values of x's. So this alpha could get out of the set I, yeah, because it could just become 0 at the moment. That's why I make a difference here and I'm summing over I prime, yes? Well, anyway, it would be 0, so, but okay. Just to notice that I prime is different than I, because I will relate to that in a moment. And then yes, and then T max I prime may be different than T max I, yeah, because this could be the largest, T alpha could be the largest of the trees that we are looking at. And we decremented this counter, so it could get to 0, and then the max of I prime is different, smaller. Anyway, induction says we can hit everything in G prime in the controlled way. So obviously what we want to do is say, okay, then we can hit everything in G in the controlled way. How do we hit it? Well, we take the hitting set from G prime and we take BL. And we claim that this is indeed the hitting set we are looking for. So first recall that BL is one of the bags in our path decomposition. And path decomposition had bags of size at most TM. Yeah. So so this would be about the size. But first, okay. But first, as I see here, I'm arguing that it's actually a hitting set. So we'll get back to the size, but we should feel comfortable about the size because we kind of just add one bag, which is exactly at most the size of one of the trees. But why do we hit what we want to hit? So the claim is that, so the induction gives us that when we remove x prime in G prime, there is no T beta for some beta in I prime. This is what induction gives us. One of the trees is not present anymore in the blue part as a minor. Let's focus on this beta, because now the claim is that when we remove x prime and BL, T beta is not a minor in the whole thing minus x. Okay, so we have to understand how could we have a model of T beta. So T beta is a tree, so it's connected. So when we look at like a model of it, it's also connected in the graph G. Now, either it would be completely in the blue part, but not, because this would be hit by x prime, or completely in the left part, but not, because this model of the T alpha was the leftmost of all the trees that the model of all the trees that we are looking at, or it's kind of across. But there is nothing across, because BL contains the interface of the left part to the rest. That's an argument. That's an argument that indeed we don't have T beta as a minor. And now it's only, we only have to agree with each other that the size of the X is really what we want to. It's not particularly difficult. Let's have a look. So the size of X is the size of X prime plus the size of the bag. Now size of X prime is given by induction. So this is this sum minus T max I prime. And the size of BL is at most Tm. Yeah, because the BL was a part of the composition given by Distel. Tm, so M was, recall that M was just the minimum of I, yeah, minimum index of I. I was this set of indices in C such that xi is at least 1, yeah. Okay, so that's the first line. Now inequality to the second line. So here the step is that because I want to relate to the sum over elements in I, not in I prime, this is what I'm changing. So I insist that I put I here. So what is the change when you move from I prime to I? And from xi prime to xi? Well, there's just one value that is different. And this value was called alpha, yeah? So this is the reason why we put here plus T alpha in the bracket with minus, yeah? Because here we count more and we subtract it here. So that's the step from here to here. And now the last inequality, this is already what we want. So why the last inequality holds? So here I remember that we have to look into cases depending on whether max I prime and max I are the same or not. So in the case that max I prime is the same as max I, all you need to observe is that T alpha is at least Tm. Well, Tm, M was the minimal index, and alpha is some index. Yeah, I'm claiming that T alpha is at least Tm. And if we agree on that, then we are okay, because max I prime is the same as max I. So I ignore this change in primes, and this this is okay to go upwards here with the inequality. Yeah, so this is one case. And the second case is when max I prime is different than max I. So let's try to imagine what had to happen. So we had this set I, and then something disappeared from it. Well, there was only one value that we dropped down. So this value had to be 1, and now it's 0. What is this value? That's alpha. That's actually, this is exactly alpha. This was this tree, T alpha here that we found in the model. And so then this means that the max I is actually alpha. And then the inequality holds because this T alpha is this T max I. And then this is greater or equal than this. And that's it. So this completes the proof of the technical statement, and of course completes the proof of the theorem itself. Yeah. So I prepared here kind of last slide. Yes, question?
Sorry, may I just take everything actually that the T, Y, T, alpha cannot be is
So it's not the alpha that we are looking at, but so you are asking again why when we remove x, then we don't see some tree as a minor, but the tree that we look at is beta. So this is not the beta. Yes. Okay. So what was well, because we have to use some information about the blue part. All we know about the blue part is from the induction call. And the induction call in this case gave us that when you remove x prime, so these red vertices in the blue part, you don't have T beta as a model there. This is what you know. And that's everything you know about the blue part. So so your claim and your only chance is to say, okay, then in the whole picture, I don't have T beta as a minor. Yeah. And the way you argue it is, okay, you don't have it in the blue. You don't have it here on the left because you don't have anything here on the left because this was the leftmost model, including BL. Yeah, that was the leftmost tree that you found as a model, including BL. So when you remove BL, the first bags from B1 to BL minus 1 just don't complete the tree as you're looking at as a minor. Yeah. And then the final argument that you cannot have a model across because all the edges across are actually going through touching BL.
Okay, good. And correctly, we were excluded. We have this four versus a minor, right?
Yeah. So okay. So you are. Yes. This is you're actually touching this subtle point, which was confusing also us when we were thinking about it. So yeah, when we look at the statement of the theorem that we're proving, yeah, the statement is either or, and the positive version, yeah, you have k-vertex vertex disjoint models, but the negative version is that you have a hitting set such that when you remove it, you don't have a forest as a minor. Yeah, that's the. But in the technical statement, yeah, what we have here is that you don't have a particular tree as a minor. This is stronger. This is stronger. That's you just in order to understand it, you hit this thing that we were kind of playing with these statements to get it right, and somewhat we could finish the induction when we have this stronger thing here. So that's actually a nice subtle point within this proof. Yeah, thanks for the question. Yeah, so I wanted to say here we have the theorem that we proved, and here is a corollary. One has to argue also that to make this transition here, but it's not complicated. Trust me. a kind of standard. What is the statement about? So you have integer p, positive, and k, and then you say that for every graph G, two options. Either your graph contains like k disjoint fragments, such that each of them has large path width, or you can find a controlled number of vertices such that when you remove them, the remaining stuff has small path width. So the large and small is in terms of p. Either you find k disjoint places that have large path width, at least p, or you can remove a number of vertices linear in k and by some function of p, such that then the path width is less than p. So we don't know. It's interesting. Yeah, we were kind of speculating if we could get it, if we could get the function of p lower. Yeah, because function of k is best possible. The linear is as always best possible here in this setup. Interestingly, you cannot get linear in k when you replace path width with truant. There, k log k keeps you holds you, and this is just because Erdős-Pósa statement itself. You can translate it easily there. Yeah. So this is a kind of funny bit. This was observed already in this paper by Gwen and Samuel and David from 2013. Yes, exactly. That's the okay. So Grzesiek sent it. So if you how should we phrase it? So the graph has tree width at least 2 if and only if it contains a cycle. That's statement 1. And now we know, or you trust me that if we want to hit all the cycles, yeah, and we don't have k pairwise disjoint cycles, then pessimistically we have to use k log k, and that's the thing. Already for this p or t in case of tree width equals 1. Or 1 or 2. It should be 2 in this statement. Well, okay. So 2 small things left. So again, what is satisfying here is that we have this absolutely tight bound for trees. We leave it open what to exactly do for forests, and already a forest with 2 components it's not clear for us what is the answer. And there is some combinatorics left to be understood there. And here, as you pointed out, Tom, maybe one could look if what is the right growth of p here. I think this 3 to the p stands for the ternary trees, exactly. Yes, okay. I tried to make it as long as possible, but still, we're okay. Let me finish it here. Thank you.